In lesson 3.4, we have two primary objectives. One is to solve exponential functions equations, and the second is to solve logarithmic function equations. They want us to use or apply a one-to-one property of logarithms and exponential functions to help us solve these equations. So we will be relying on the one-to-one property to help us solve them. First thing we want to do is visit a little bit about what it means to be a one-to-one function. Back in our beginning stages, we talked about one-to-one functions. A one-to-one function is any function that can pass both, first of all, the vertical line test, and then if it passes the horizontal line test, it's a one-to-one function. So what I'm graphing in red here is an exponential growth model. So it's y equals, and it could be any base as long as it's bigger than 1, so 2 to the x. This is an exponential growth model. This is a function because it passes the vertical line test. No matter where we put the vertical lines, it will always touch it once. And this same graph will also pass a horizontal line test. Now the horizontal line test is what we apply to our graphs if it was going to be one-to-one. The important thing about one-to-one functions is no matter where you place that horizontal line, it touches it just once. And in our definition of a one-to-one function, it says for every input, no matter what that input is, so whatever it is, it has one output and only one output, which is a y value. And this ordered pair, this correspondence would be unique, so that no matter what the exponent is, x, there's only going to be one anti-logarithm, one y value that corresponds to it. So therefore, when we find the inverse function, and the inverse functions are the logarithms, then we can find one exponent that corresponds to the anti-logarithm, one anti-logarithm that corresponds to the exponent. So these things can help us figure out missing values in equations. And here's the summary that they have for the one-to-one property of exponential equations. It's really quite simple. And they say in words that really if b to the x, no matter what the base is, equals b to the y, as long as these bases are the same, the only way these two statements can be equivalent is if the exponents are also equivalent. Okay, this goes into that one-to-one idea that if we raise some power, like 2 to the third power, it's got to be equal to 8, and it's only one output, 8. So if this is a 2 to the third, and we're wondering what we raise 2 to get an identical value is, it has to be 3. So that's where they say, then x has to equal y. We're going to use this to our advantage to help us solve some exponential equations. Here's some examples of this. They want us to solve these exponential equations by using the one-to-one property. Well, the one-to-one property says if we have the same bases, and that's our first dilemma here. Our bases are not the same. But in these problems, what you will see is that you will be able to convert one of the bases into another base. And typically, you convert the larger base into the smaller base. A 16 can be converted into a base 4 if we think of exponents. So what I'm going to do is I'm going to convert the 16. 16 is 4 squared. Now 16 is 4 squared, and that was raised to the x plus 3. So really, all I've done is I've renamed 16 as 4 squared equals 4 to the 4x plus 7. Now we're going to use some exponent rules. When you have a power raised to a power, our power to power rule says you multiply exponents. So this is really 4 raised to the 2 times x plus 3, which is equal to 4 to the 4x plus 7. And I'll make one more simplification in this. This is equivalent to 4 to the 2x plus 6, and that has to equal 4 to the 4x plus 7. Now here's where the one-to-one property comes into play. The only way that these two expressions can be equivalent is if the base is the same on both of these, then the only way they can be equivalent is if the exponents are the same. So what we simply do is we equate the exponents and go 2x plus 6 has to equal 4x plus 7. And if that's the case, then we'll solve this linear equation by moving the 2x over. So we'll have 2x there, move the 7 over, which will give us a negative 1, and that means x has to equal a negative 1/2. If x is a negative 1/2, then our original problem up here is going to be equivalent, and we can plug it back in and check. I'm going to bypass that for right now, but that is how we solve these equations using the one-to-one property. Now here's another example that we can try. This one's a little bit more complicated, but hopefully what you can see is that there is some commonality between those two bases. In order to use the one-to-one property, you want the bases to be identical. But this 2/3 is not identical to a 9/4, but I do see the connection between them because the 9 is 3 squared and the 4 is 2 squared, so I can see the 3 and the 2 permeating through that idea. Now what we got to do is we got to get it flipped. So there's a couple things here that needs to be done. Number one, I want to reciprocate this value. The only way we can reciprocate that value is to raise it to a negative power, so it's negative 3x to the 4. Next thing I want to do is I want to rewrite the 4 and 9 as factors of 3 and 2, so the left side is going to stay the same, equals 4 is 2 squared, 9 is 3 squared, and that's raised to the negative 3x over 4 power. Okay, so now we're still trying to get it to the same base. I want the base of 2 over 3, not 2 squared over 3 squared, so I'm going to leave 2/3 here, raised to the x minus 5 equals. Now I'm going to use this power rule of exponents. I can rewrite this as 2 over 3, and I can bring out the power of 2 out of both of those, 2 to the negative 3x over 4. So this is our power rule of exponents. If it's a power raised to a power, then we multiply exponents. So I just kind of use that in reverse to get that 2 out of there. So now we have something that's pretty close to what my final product is going to be here. It's 2/3 raised to the x minus 5 equals 2/3 raised to the, and now I've got, this is 2 over 1, negative 6x over 4. Now here's where we use our 1-to-1 property. The only way that these two quantities can be equal if they have the same bases is if the exponents are equal, because when you raise a base to an exponent, there's only one possible outcome. So we have x minus 5. We can reduce this to a simpler idea. If the bases are the same, the exponents have to be the same. Therefore, the x minus 5, that exponent has to be the same as a negative 6x over 4. And we're going to solve this resulting linear equation. So to solve this, the first thing I'm going to do is multiply both sides times by 4. So it's 4 times x minus 5 equals a negative 6x. Then I'm going to distribute the 4. So 4x minus 20 equals a negative 6x. And then however you want to rearrange it, to me it's easier just to bring the negative or the 4 over by subtracting. So you got negative 20 equals a negative 10x, which means x is going to have to equal a 2. So whenever they refer to this 1-to-1 property of exponents, what we want to do is we want to ensure that our bases are going to be the same. So we want to come back and say if the bases can be the same, then we can force the exponents to be the same, and it gives us a tool or a strategy for solving exponential equations. So that's the first idea in lesson 3-4.